Alright, in this video we're going to extend our discussion, no pun intended, on abstract classes by designing a very small programming language. So this is actually a language that I call ASPL, which stands for a simple programming language. And the way it works is, let's first think of some expressions that we might write in this little programming language. So let me give you some examples of expressions. So let's say we have some type of expression that looks like this. Okay? What do you think this does, just intuitively? Well, if we interpret the plus as addition and then these as operands, then this expression probably resolves to 42. And indeed, it does. Okay? Let's think of another type of expression. So let's say we have an expression that looks like this. So what do you think this does? Well, it probably, if we're saying let x 41, it probably says, okay, we want to assign x to be the value 41. Okay? And that will hold true for everything inside of the let expression. Okay? So inside of this block, effectively, there's a value called x that's bound to 41. Okay? Then in this block, we have another, let's use a different color. Here we have a let expression that says let y be bound to 10. So in this block, this orange block, we have a variable that says y is bound to 10. Okay? So then this expression, this is a times if you're confused about that. This says we're going to multiply the variable x by the variable y, okay? Or multiply x with y. So what we do is we look up to see what the value of x is. So we say, is x in the current scope, effectively? And the answer is no, so we go up a level. So is x in this level? The answer is yes, it's right here. So we replace the x with 41, and then we do the same for y. So the value of y is in the scope, which is bound to 10, so we replace the y with 10, and then we get 41 times 10, which is 410, so the whole thing resolves to 410. Okay, let's do one slightly, well, not harder, but yeah, let's do something similar. So we'll do x to be the value 10, the value, or the variable y to be x times 2, and then we'll do if, let's see, less than x 15, 42, let's do 0, 42. Okay? So how does this work? So similarly, we have a let expression that binds x to 10. So in this scope, we'll put a block around it, we'll say that x has the value 10. Okay? And then, so that's an x, not an alpha. And then inside of this scope, with this if, we say that y is bound to x times 2, so we look up what x is, and it's 10, so we get 20. Okay? So, let's do y instead of x. Okay? So here we're saying if y is less than 15, then we're going to return 0, otherwise we're going to return 42. Well, to evaluate this if, we need to evaluate the predicate, the condition, right? So we do, so is it true that y, if we look up y, that's 20, so is it true that 20 is less than 15? The answer is no. So we do not evaluate this branch, we evaluate this branch, which is just the value 42. Okay? And we'll do one more expression just to showcase something. So let's say we want to do the sum of these two sub-expressions. Okay? So if you want to compute the sum of these two expressions, then we have to recursively evaluate those expressions, right? So in order to do this plus, we have to do the product of 4 and 3 and the product of 2 and 3. So we get 4 times 3, which is 12, and then 2 times 3, which is 6, so the whole thing returns 18. So, where have we seen this before? We saw this when we were doing the ASPL interface, right? And we drew this as a tree, right? So we said, like, we have a plus, which has 2 components. We have 2 times is here, and then we have a 4 and a 3, and then this has 2 components, which is a 2 and a 3. Okay? So this thing, this diagram here, is actually something that is called an abstract syntax tree. Okay? And effectively what that means is we have a node or an element in this tree that represents some form of syntax in our program. Okay? Now, it doesn't say, so this isn't really an abstract syntax tree, this is more of something called a concrete syntax tree, but what we could do is rewrite this to say that this program here is represented by an add expression, which has 2 mul expressions, which then has 2 num expressions, and then these num expressions are represented by the values 4, 3, 2, and 3. Okay? So this is an abstract syntax tree, okay? Because it describes the structure of the syntax of our language as a tree. Okay? So what we're going to do is similar to what we did with the ASPL interface. We're going to do something similar, except we're not going to use interfaces. We're going to use classes, okay? Or I mean, we're going to use a class hierarchy to define the nodes of our programming language, okay? So, let's go over to IntelliJ. So, what do we have here? Well, the first thing we need is some way of representing an abstract syntax tree just generally, okay? So, as we sort of saw with the animal example in the last video, there's a way that we can represent an idea of something that cannot itself be instantiated, but it has classes, subclasses that can be instantiated, okay? And we said that that was an abstract class, and indeed we're going to make a class called AST that is abstract, okay? So we're going to have a whole bunch of, well, not a whole bunch, we're going to have several classes that extend AST and build off of its capabilities, okay? So the question is, what properties do what properties do abstract syntax trees have? And that is, they have children, right? They have, so if we go back to that AST that I erased, so we had like add, and then this has mul, and then this has num, blah, 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 blah. We see that we can represent these as children of this AST, okay? Now this isn't quite how we're going to structure our operations here. Like add and mul are actually going to be coalesced into one class, but the idea is effectively there, right? So an AST is going to have a list of children, okay? And if I could type, that'd be great. We're going to make it a final list, okay? Because once it's instantiated, there's no need to change it from that point. I mean, yeah, we can add things to it, but the list itself is not going to change, okay? So let's create the AST constructor, and what we'll do is we'll actually pass in a variotic number of children, okay? Because certain subclasses are going to have more children than others, and some may have a variable number of children. So for example, a primitive operation like mul and add can actually have multiple children. Like it can do 2 and 3, but it could also do 2, 3, 4, 5. It could be variotic, okay? Additionally, some classes have a fixed number of children. So for example, if we'll have 3 children representing the predicate, the consequent, and the alternative, okay? And then some actually don't have any children at all. So for example, the num node won't have any children. It will just represent an AST that stores some number inside of it. Similarly, there will be a bool expression which represents either true or false. Okay? And we'll see why we need bool. Well, we don't really need bool. You could represent this with just nums. But we'll see why having bool is nice, I guess. Okay? So, in the constructor here, we'll say this.children equals new array list. And then we'll just say for every AST in the array, we'll just add it to the array list here. And yeah, I mean, we could do collection.addAll, but I don't really care. Okay? Now, let's write an accessor method. So, an accessor method for actually getting the ith child. So, we'll say getChild, and then we'll just say return this.children.getIndex. Okay? Return this.children.getIndex. Okay? Good. So, I mean, we can also do, like, get all of the children, so we'll just have that just in case we need it. But the main thing we're missing here is a way to evaluate an AST, right? A way to evaluate an AST. So, how do we evaluate an AST? Well, we don't know, right? Because an AST is abstract, right? So we don't know how to evaluate an AST. We do know how to evaluate children of an AST, or subclasses of an AST, but we don't know how to evaluate just an AST. Okay, and that's the important thing. So let's do that. Let's write the abstract. So what are we going to return? We're going to return an AST itself, and we're going to call it eval. Okay, and the reason why it's going to be an AST is because this is just how we're going to structure the program. So, but we'll see what this actually means once we start writing the subclasses, which will be right now. Okay? So, let's do the two simplest classes. We have num and we have bool. So, num is going to, of course, extend the AST class, and then the constructor will look like this, but we need to pass it a number. We need to say, like, what number this num node represents. So we'll give it a number, and then we're going to call the superclass constructor with no arguments, but then we're going to assign into an instance variable. Okay? Just like that. And then we'll say we can get the value by doing this, and then we can also, this is the important part, we're going to eval this num by just returning itself. Okay, returning itself. So the question is, what does that even mean? Well, numbers resolve to themselves, right? Like if you type in, let's say that you're writing in Python, okay? In the REPL, if you type a number, 42, you're just going to get that number back, right? So numbers just resolve to themselves. There's no way to further reduce a number, okay? And interestingly, the same thing holds true for Booleans. So, we could actually just copy and paste everything and just change it to Booleans, okay? Now, a better way to do this would be to have a class that's called, like, literal or something, and then you can parameterize it over the integer or the Boolean wrapper classes, and then you wouldn't have as much redundant code, okay? But I'll leave that as an exercise to the readers. And if you want to know how it's done, it actually is in my book. So you can, if you're unsure how to do that, you can look at the book and you'll see from there. Okay? Good. So now let's do an interesting one. Let's do primop. Okay? So primop is going to extend AST, and a primop is going to have some number of children, but it's also going to have a string representing the operator that it represents. So for example, plus, times, less than, or something like that. Okay? So it will receive the operator as a parameter, and then it will receive the variotic number of arguments as the second parameter. Okay? Well, everything after the first parameter. And we'll pass those up to the superclass constructor, and then assign the operator to the instance variable. Okay? Very good. Now, this is actually the really interesting part, because we need to know how to evaluate a primitive operation. And the question is, how do we do that? Well, one thing we saw was that, at least with that very last example, we said that when we evaluate that plus of times operations, we have to first evaluate the operands and then apply the operation. Okay? So the very first thing you do whenever you're evaluating any primitive operation, whether it's a less than or a plus or a times, you have to recursively evaluate the arguments. Okay? So this even holds true for something like a less than. So if we're saying this, like if we're saying less than this versus 6, you can't say that a prim operation, or a primop, because this would be a primop, and this would be a num, you can't compare a primop to a num. You have to recursively evaluate this primitive operation to get less than 5, 6, and nums evaluate it themselves. So, yeah. So then you get num, num, and then this would be perfectly fine. Okay? So, how do we recursively evaluate the arguments? Well, this is actually very straightforward. All we have to do, we're going to create a list, and, well, if IntelliJ would, okay. Yeah, so we're going to call it eval args. Now IntelliJ listens, great. And what we're going to do is we're going to get that list of children. Remember that list of children? That accessor that I made? We'll do this.getChildren, and then we're going to map. We're going to convert it into a stream, and we'll map over, so what does this lambda expression receive? It receives an AST, and it returns an AST. Okay? So, we're going to do T for AST, and then we're going to call T.eval. Okay? So this will evaluate all of the children in the getChildren AST, and then that will return a stream, which we can then convert into a list. Okay? So, if you don't remember how map works, you could also do this with a for loop. That would be fine, but I think that the stream API makes this very nice. Okay? So, we evaluate all the children, and then we get the evaluated list of children. Okay? Now, we need to do a case analysis on the operator. Okay? So, the painstaking way to do this is to just do like if this.op equals plus, if this.op equals less than, and that's what we're going to do. But a much better way to do this would actually be to have something like a hash table, where you have the operand, and then you have a function interface, remember that maps the operator to a function that gets called that is basically a case analysis on the operator. Okay? So what do I mean by that? So what I mean is, let's say we want to write the private AST eval plus, and it receives a list of args, and then we'll have private AST eval less than. So there's no getting around having these methods. I mean, yeah, you could put the code in here, but there's not going to be any way of getting around having to handle these operations separately. Like, you can't evaluate a plus the same way you evaluate a less than. It's impossible. Okay? But let's first write these methods, and then we'll see what we could do to make it a little bit easier. Or rather, we'll write the methods, write the eval method for primop, and then I'll talk about how you can make this part a little bit, well, a lot nicer and more flexible. Okay? So, how do we evaluate a plus? Well, we're going to need to do, first of all, we're going to need to create a number that just stores the result. Okay? And because we're returning an AST, we can do return new num that wraps the result that we have here. So actually, I'll call this sum instead of num. just to make it a little bit clearer. Okay. Now we're going to loop over every AST, and now the question is, how do we get out? So this is going to be an AST of num nodes, right? It has to be, right? And why does it have to be? Because we know that when we recursively evaluate the children of like a plus, so something like this, so this is going to have to be recursively evaluated to be, or to become, plus 5, 5, right? Now, I'm going to assume that all programs in this language are well formed, so that means like we're not doing like plus, less than 2, 3, 5. So I'm assuming that the program is well formed, because this would then mean plus true 5, and of course that would be nonsensical. Okay, but more importantly, that would mean that this is a bool and that this is a num, and that's not good. Okay, this is a bool and that's a num, so that's bad. So what we can do is just assume that the input program is well typed, meaning that all expressions are like, you're not going to be adding a boolean and a num. That's basically what I mean. Okay, so what we can do is safely cast each of these AST nodes into a num node. Okay, so this will never fail if the program is well typed. Okay, and once we have that, we can do sum plus equals num dot get value. Okay, sum plus equals num dot get value. And then we're done. That's it. That's all we have to do. Okay. Now, what we're going to do, evaluating the less than operation, this is actually going to be a little bit more powerful than Java's less than operation. What we can do is, first of all, we're going to assume that there are at least 2 arguments. Okay? But what we can do is further assume that we can pass in multiple arguments. So what this will do is it will return true if everything is less than its successor. Okay? So actually, I'll leave that as an exercise to you, but what we'll do is we'll just assume that there are only 2 operands, and the first one must be less than the second one, but extending it to beyond this, to have multiple operands, is very straightforward. Okay? So this would mean that this would return true, but if we did 2, 3, 2, that would return false, because 2 is not less than 3. Okay? Good. So we'll say int first, or rather, yeah, that's fine. Int first equals, so we'll cast this to be, or we'll cast the first to be a num, and then we'll get the value. Int second, or let's do right hand side. Left hand side and right hand side. So num args.get 1. Let's do get 0 and get 1. Dot get value. Okay? And now we can return a new boolean that represents whether left hand side is less than right hand side. Okay? Now again, you need to make this a lot more flexible. You use a for loop, of course, to handle multiple arguments, but again, I'll leave that as an exercise to you. It'd be a very simple exercise to complete, and it'd be kind of cool to see something that's more powerful than what you can do in Java, because in Java you have to do something like combine everything with a logical AND operator, and that's a little bit verbose. Okay? Good. So, now let's talk about how to evaluate primop. Okay? So, how do we evaluate a primop? Well, we're going to do a case analysis on the operator. Okay? So, if it's equal to a plus, what do we have to do? We just call the evaluate plus method and pass it eval args. If it's equal to the less than, we call eval less than eval args. Now, hopefully you can already see that this is kind of verbose and can be prone to errors. And if you want to update or add an operand, or an operator, excuse me, you have to update the case analysis, and you have to update you have to write the method itself. Okay? So what you could do as an exercise, and this is actually an exercise in the book, you can create a hash map of function objects operations like plus, and map those in a hash map to their function. So like eval plus, and then less than would be mapped to eval less than, so on and so forth. And you'd only have to update the hash map. You wouldn't have to create a new case analysis. Okay? And then this method would literally be something like return this dot operations map dot get. Then you pass the operation or the operator, and then just call the method that it returns, and then pass it the evaluated list of arguments, and that's it. And then you'd never have to touch this method again, and it would be very, very clean. So that's a great exercise to do, and I would strongly encourage that you do it. Okay? Good. So now let's do if. So I was going to do variable bindings with let, but I think this video is getting a little bit long, so I'm just going to do if, and then we'll call it from there. Okay? Now, if is actually very straightforward. So primop is definitely the hardest. If is by far, well, not by far. It's the easiest compared to num and bool. Okay, I'll say that. Okay? So, it receives an it extends an AST, and it receives 3 ASTs. It receives a predicate, a consequent, and an alternative. Okay? And we can just pass these up to the superclass constructor. Why? Because that constructor is variotic. Remember we said that this is variotic, so we can pass in any number of children. Okay? And then that's it. That's all we need for the constructor. Now, all we have to do is just override eval. So how do we override eval? Well, we evaluate the predicate, and if the predicate is true, we evaluate the consequent, otherwise we evaluate the alternative. Okay? So, how do we evaluate the predicate? Well, the predicate is the first child, right, at index 0. So all we have to do is say AST pred eval equals this dot get child 0 dot eval. Now, how do we know that this returns? Well, so with an if, the predicate must be something that resolves to a Boolean, and that kind of makes sense. So again, we're going with the assumption that the programs are well formed. So for example, I'm not going to write something like if plus 42 042. Okay? So these are fine. This is obviously not fine because that does not become true or false. Okay? So, what we can do is we can safely assume that this is a Boolean, or a bool node. And in fact, we're just going to go ahead and cast it so it makes it easier when we're writing the predicate. Okay? Or like using Java's if. Okay? So, if the value is true, then we're going to evaluate the consequent. Otherwise, we're going to evaluate the alternative. Okay? So how do we evaluate those? Well, those are the second and third children respectively, indices 1 and 2. Okay? So return this.getChild1.eval, return this.getChild2.eval. Okay? And that's it. That's all we have to do. Now, let's test this and see what we can do. Well, let's first create that very simple program. So I'm not doing unit tests here. I'm kind of feeling a little bit lazy. So we'll just write them in the main method here. So, but actually that means that we'll need to override the toString methods to get something useful here. So if we're wanting to get the, like if you want to print out a number, we're going to convert it to a string and then output that. And for Boolean, we're just going to convert that to a string by just printing out the, like, either true or false for the, whatever the value is. So return boolean.toString this dot value. Okay? Very good. So, and the reason why we can do that, and we don't have to do that for primop if, well, primop or if, is because no program is going to just be an if or a primop, because it'll reduce to either a num or a bool. Okay? Some kind of atomic value. Right? Okay? So good. So now let's see what we can do. Let's do new primop, and we'll pass in a plus, and then the operator, the operands, excuse me, we'll do, let's do 4, and then new num 39, let's do 38, and we'll output t1.eval. This should be 42, and it is. Very good. So let's do AST22 equals new if. So let's say, let's write this out in the little parenthesized language that I did before. So say if the sum of 10 and 20 is less than the product of, well, we don't have products, so it doesn't matter, is less than the sum of 30 and negative 5, then we'll return the sum of 8 and 5, otherwise we'll return the number 0. Okay? So, how do we do that? Well, we can do new primop less than, and the operator, the operands, I keep getting this backwards, is a primop itself with two nums, 10, new num 20, and we're checking to see if that is less than the primop of plus, new num node of 30, new num node of negative 5. So if this is true, then we're going to do new primop plus, new num of 8, new num of 5. Otherwise, we're going to do new num node of 0. Okay? Now, because 30 is not less than 25, this should output 0 when evaluated. Yep, and it does. Okay, so what we've done here is actually something very powerful. Okay, we've written a very small amount of code to describe a very, a small, admittedly, but powerful programming language. I mean, we've written something that can have conditionals, numbers, booleans, and some simple primitive operations. And it would not take very much at all, and you can read in the book about this, to support variable bindings. Okay? So, one thing we could also do is label these classes num and bool as final. We can actually label everything as final, because there's no need to extend these classes, right? Num, bool, primop, and if should not be extended. At least I don't think they should be extended. Okay? Okay. So, I hope the exploration of abstract classes was interesting, and this ends Chapter 4.